Okay, this is our video lecture for 12.2.2. Today we were going to build some polyhedra, and we were going to try to find out if there's some pattern to maybe the number of sides, that like comparing the number of faces to the number of vertices to the number of edges of all different kinds of polyhedra, because it turns out there is actually a little rule that kind of guides this, that kind of you can use to find out how many, if you know how many faces and edges, you can find out how many vertices. So what we were going to do is we were going to test just a bunch of random polyhedra, ones that we made. We were going to try to see if we could make some that don't follow the rule. We were going to make a whole bunch of them and, you know, see if all of them follow this rule. And also we were going to try to figure out what the rule is. So, so does it usually, so the question is, does the polyhedron usually have more faces or more edges or more vertices? When I first saw that, I just wanted to ask myself, on a cube has 6 faces, and how many edges does a cube have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. So a cube has 12 edges. Maybe I should start a little list. Cube. Faces, edges, vertices. A cube I know has 6 faces, and didn't I just count the edges? What was that? 8, 12. 12 edges. So the toothpicks are the edges. Okay, so how many? Basically, if I couldn't count them, I could just take this thing apart and I could lay out the toothpicks and count how many, and that would give me the edges. How many vertices? Well, I have a cherry ball at each vertex, so 2, 3, 4, 5, 8. Let's try something else. This thing is a tetrahedron, I think. So how many faces does it have? Or in other words, if I did make it out of like cardboard, how many cardboard triangles would I have? 1, 2, 3, I think I'd have 4 faces. Tetrahedron. And then how many edges would I have? 1, 2, 3, 4, 5, 6 edges. I counted the popsicle sticks. And how many vertices would I have? 1, 2, 3, 4. 12, 8, 4, 6, 4. That's interesting. Okay, so let's try something else. What's this thing called? This, I think, is called an octahedron, because it's got, I know it's probably hard to see in the video, but it's actually it's made out of 8 triangles. So it'd have 4 on the top and then 4 on the bottom. So it's got 8. It's an octahedron. How many edges does it have? How many toothpicks do I have here? 1, 2, 4, 5, 6, 7, 8, 9, 10, 11. I got 12 again. Huh. And how many vertices do I have? 1, 2, 4, 5, 6. Okay, so I know that my video can only be less than 10 minutes long, so I'm going to kind of, let's pretend that I got some more data from a few more of these. And then let's see if we can find, so let's see, faces, vertices, edges. It says create a table like this one. So my table's kind of like that one. Look for a relationship between the numbers in each row of the table. Try adding, subtracting, or both the numbers to find the pattern. Now, I'm going to we don't have that much time, so I'm kind of going to spring it upon you. It turns out that, if you haven't figured it out yet, you can take the vertices minus the edges plus the faces, and that should equal 2. Now that seems like it came right out of the blue, and I think that you guys would have discovered that in your groups as you I think if you did enough of these polyhedra, and you looked at the numbers, you know, and tried enough things, I think you would have actually discovered this on your own. But I'm kind of, for the sake of time, I'm kind of just telling you. But let's test it now. So this one has 8 vertices. How many edges? 12 edges. This thing better work. 6 faces. That better equal 2. Let's see. 8 times 12, or 8 minus 12, that's negative 4 plus 6. Hey, it does. So that one worked. What's my vertices? 4 minus edges plus the faces. That equals 2. So it seems to be a pattern that's holding true so far. Vertices, 6 minus 12 plus 8. So I can just go that minus that plus that. Should equal 2. 6 minus 12, that's negative 6 plus 8. Okay, so I need you to do whatever it takes, you know, maybe draw a few. You can draw some of these and convince yourself that this is true, and then you're basically just going to answer questions knowing this. This is called Euler's. This guy named Euler, Leonhard Euler. I guess that's supposed to be a picture of him right there. It's named after him, and it's called Euler's formula for polyhedra. Okay, so you can read this. It's very interesting. So let's see if we can answer a question. If a polyhedron has 5 faces, I'm going to just keep talking until my 10 minutes are up now. If a polyhedron has 5 faces, let's write his formula up here first. That's his formula. So 1269A says it's got 5 faces, so I'll put a 5 in underneath faces, and it's got 6 vertices. How many edges must it have? Well, I don't know. I'll just do some algebra on it. You guys probably don't need to do algebra. Maybe you can just do some arithmetic on it, right? The 6 and the 5 make 11, and 11 minus something is 2. I'm thinking 9. 11 minus 9. I think if that was 9, I think E equals 9. It has 9 edges. So that's pretty handy, right? So I got 2 more minutes left. What if a polyhedron has 36 edges? Okay, so let's just keep doing this. Where's the edges? 36 edges. Here's letter B. 14 faces. Faces. It's going to ask us how many vertices, right? How many vertices? Well, okay, negative 36 plus 14. I don't have my calculator. I should be able to do this in my head anyway. So, is it 12? No, 3 minus 1 is 22. So that's negative 22. I think this makes negative 22. I'm kind of useless without a calculator, unfortunately. If I add 22 to both sides, then I would get 24. Hopefully I didn't make any mistakes on these. I don't have the answers in front of me. But do you get the idea? We're plugging in, this is our magic Euler's formula, but it's not magic because we discovered it. Well, you can pretend that we discovered it on our own as we built these polyhedra. I'm still recording. Okay, and I guess that's enough for now.